that's a complete failing for that not to have been covered. Right. So it's just awful. Right?
F. Trying to get an F.
Yeah. So I'm going to walk you through how it's constructed. I'm going to kind of take you through some of the Desmos applications of it, because it's kind of no, it's not really an application. It's more like the derivation, right? So what we have here is a circle. I mean, in this mess somewhere, there's a circle, and that circle has a radius of 1, right? So that unit circle, the unit part of unit circle, it's called that because it's a circle of 1 unit, right? With a radius equal to 1. All right. So that's something. Now, I can graph a circle. There's a few different ways that I can graph a circle, whether it's on Desmos or other forms of technology. One way would be using the formula, or well, it's not really a formula, but it's an equation: x squared plus y squared is equal to 1, right? But that 1 is actually the r squared value, right? So this comes from x squared plus y squared is equal to r squared, right? So this is a circle with the center at the origin, and radius equal to 1. I'm sorry, radius equal to r. The one below it is the particular, right? Radius r. All right. So if I put that in Desmos, x squared plus y squared is equal to r squared, and then add a slider for r, I get a circle. And in this case, with the r value being equal to 1, it gives me a circle with a radius equal to 1, right? Now, if I make my radius equal to 2, if I can get it onto a 2, it modifies the equation, but it also modifies the graph, right? And that should make sense, right? If you increase the radius, you're going to increase the size of the circle. I mean, that part should be easy enough, right? But in this case, we're only focusing on a radius value equal to specifically 1, right? But we need some points around this circle. Now, some of them are easy to come by, some of them not so much, right? So they're, like I tend to say, there's a few ways to handle this. One way is just, go around the circle and estimate some points. You get these disgusting decimals along the way, but those decimals actually correspond to particular radical values. These are all irrational numbers. And so there is a more exact way of representing these values. And so what we want to do is try to kind of grasp onto these. All right. So we're going to kind of do a hybrid approach. That word kind of terrifies people after the last year. But an approach, half technology, half by hand, right? So starting off with a point on the x-axis, that's 1, 0. That's easy enough. That's the point right here. But when you're working your way around a circle, you have the linear components, horizontal movement, vertical movement. Every coordinate around this circle can be thought of as an x value, comma, a y value. But all these points could also be considered based off of the angle in relation to the x-axis, right? And so that's where things get a little funky, right? And unfortunately, that's where the journey starts kind of getting more complicated. All right. What we do is we define to the right as 0 degrees. All right. Now that's one thing that I never really liked, although it makes the math work out nicely. It doesn't really work out with the way everything is laid out in real life, because 0 degrees is due north. I have it pointing due east. So there's already a kind of a structural difference there, right? But you learn the rules of the game, and things get a little bit more magic, right? As you work your way around a circle, you do a 360 dunk, if you're playing basketball. You spin around in one full turn and then you jam it home. Well, that's one full turn around a circle. That's one full turn around a circle, giving us 360 degrees. So I have the beginning and the end in terms of angle measurements, right? So what's happening here is I'm starting off in the easterly direction is really all I can say here. And then I'm taking that angle and really just kind of moving it around in a counterclockwise fashion, so I can kind of pin that at the origin here. So I'm moving it around in a counterclockwise fashion, and it's creating a circular movement, right? That circular movement, if it's periodic in nature, in the sense that it's a repeating pattern. So I would start off at 0 degrees, and then I'd work my way around. And eventually I'd complete one full turn. That would get me to 360 degrees. All right. So that's the movement that we're looking at here. But we need to come up with the math behind. All right. I guess I can leave this here. Looks kind of cool. So in terms of some of the movements, some of them are a little bit more obvious. Like, for example, this is going to be 90 degrees because that's a quarter of a turn. Right. So just going back to my diagram here. Size. If I make this movement, I know it keeps shifting on me, but it's going to be a quarter of a turn. Right. I didn't go all the way around. I only went a quarter of the way around. So if I'm going a quarter turn and all the way around is 360 degrees, a quarter of that would be 90, because 360 divided by 4 is 90. All right. If I go halfway around, I've gone 180 degrees. All right. If I go 3/4 of the way around, maybe use a calculator for that. 0.75 or 3/4 times 360 would be 270. But you could also look at it like this. If I say that this movement here is 90 degrees, and that was a quarter of a turn. Well, I'm going to do 2 more of those quarter turns. All right, so that's another 90 to get me to 180, and another 90, 180 plus 90 would give me 270. And then if I wanted to do 180, 270 plus 90 again, that would get me right back to 360. So those are what we call the quadrantal angles, right? Anything that lands on a quadrant, right? Because this would be the x-axis here. And we'd have this being the y-axis here. Anything that falls on either of these two axes would be known as a quadrantal angle. All right, so I'll just make a little note of that. Just jot that down on the bottom. Any angle that falls on an axis is quadrantal. I don't even know what I'm trying to write there. I was trying to make it all caps, but it wasn't looking good. So quadrantal. The quadrantal. Quadrantal. Quadrant. However All right. It's a word that comes up fairly frequently, so it's worth mentioning. I mean, I'm not usually too much of a stickler when it comes to vocabulary, but this is kind of an important one. You know, when it comes to trigonometry, you'll find that the vocabulary here is a little bit more important because there's a lot of different ways to think about trig, and we want to make sure that we're all thinking about it the same way when we're having a conversation about it. And in a lot of ways, having a conversation is you answering one of my questions on a test and me grading it. So you want to make sure that you're at least speaking the same language I am, the language of trigonometry, right? And that involves the vocabulary, right? Just like I guess any other language would. So we need to start working our way around this circle here. This actually calls back on some important geometry relationships. This wouldn't even have been covered in the last course. It would have been covered courses ago, right? Maybe even in middle school or early high school. And that has to do with different right triangles, right? One of those right triangles is a 30, 60, 90 degree right triangle. And another is a 45, 45, 90 right triangle. I'm going to write this down in a sec. But these are our important right triangles because they have known ratios associated with them that can be translated to a lot of really important trigonometric applications. All right. So let me just kind of off on the side here, jot down or sketch out anyway, a quick diagram. I'm just trying to get it to be roughly symmetric. All right. So I was going to say good looking triangle. Didn't really play out the way I wanted it to. I'm going to try that again. Do a nice job. All right, that's better. All right, I wanted it to look equilateral. All right, all three sides congruent. In an equilateral triangle, all three sides are congruent, but all three angles are congruent. And if all the angles in a triangle add up to 360 degrees, then each one of these angles has to be 60 degrees. All right. So then what I'm going to do here is drop an altitude. Now an altitude forms a right angle with the base, right? It also bisects the vertex angle. So that angle up at the top, that gets cut in half, becoming two 30-degree angles. Right. So we get a 30, 60, 90 right triangle out of this. All right. What we're going to do is really just kind of invent on the fly the relationship between all the different sides of this triangle. All right. So this becomes a 30, 60, 90 right triangle. But it's really just a 30, 60, 90 triangle because the 90 is what makes it right. All right. So what we do here is we just define the lengths of the sides as something completely unknown. Right. But we have a couple of different unknowns that we could be looking at here. Right? I got the unknown legs of the triangle. But then I have these two unknown pieces on the base here and here. All right. An altitude bisects the base, which guarantees that these two line segments have to be equivalent in length. So whatever this one is has to be the same as that one. All right. So then if I call this one X, for example, then this one has to be X also. Yeah, that's because they're equivalent in length. All right. Now, if each piece is X units long, then in total, we'd have 2X. All right, because X plus X is 2X. You just add them together. All right, they're two like terms. I don't know either of them, but I do know they have to be the same. So I call one x, and if they're the same, I call the other one x, right? So then because of that, and the fact that this is an equilateral triangle, all the sides have to be congruent or equal in length. So each one of these sides is going to be equal to 2x, all three sides of the triangle. All right. So then what I can do is focus on just one of them. Because the only thing that's left to figure out really is the altitude, the length of that altitude. All right. So I'm going to abbreviate that with an H for altitude, of course, height, you know. So I can apply the Pythagorean theorem here, and just focusing on this one triangle, if I can actually draw a triangle, there we go. Just focusing on that one triangle, just so we kind of clean up the clutter here a little bit. I can solve for the value of, well, whatever I want, but I'm going to solve for H here. All right. All right. So Pythagorean theorem tells me, you know, a squared plus b squared is equal to c squared. I can say x squared, I'm going to make this smaller, x squared plus h squared is equal to 2x squared. So x squared plus h squared is equal to 4x squared. I can subtract off the x squared from both sides because it's a like term. And I get h squared is equal to 3x squared. But I want h, so I would then take the square root of both sides. And so take the square root of both sides, and I'm going to get h is equal to, this would become, well, the square root of 3. You can't do anything about that, but the square root of x squared, that part I can do something about, because the square root of x squared is equal to x. So that tells me that the length of this side in the 30, 60, 90 right triangle would be radical 3 times x, or x radical 3 if you want, either way. And we're going to need this information in a minute. So, you know, in the past, I wouldn't even review it because, again, it's supposed to be something covered pretty extensively in college algebra with trig, but if it's not, then it's got to get covered. Because there's no, honestly, without the unit circle, there is, and again, I don't know where everybody ends up after this, but there is zero, and I mean 0 chance of being successful in Calc 1, 2, or 3. Like 0. And I don't succumb to exaggeration. Like, there is no universe in which you will be successful in the math classes that follow this one without knowing this information. All right. So, I'm not a fear monger. That's the reality of it. All right. So we're going to apply that now. At this location here, we're going to call that 30 degrees. And I'm going to draw a triangle. All right. So what I'm going to do is I'm going to draw a line segment going from 0 degrees to the circumference of the circle, and I'm going to drop an altitude. Now, what's happening here is our angle is sweeping through a 30-degree, what we call a reference angle. All right. So we've just moved 30 degrees to get to this location. Starting at 0, we move 30 degrees. All right. And then in a couple of minutes, we'll move a little bit more and a little bit more and up to 90 degrees. But for now, we're just moving 30 degrees. All right. So that means that the angle at the origin has to be equal to 30 degrees. So this angle here is 30 degrees. If we know that this one down on the x-axis is equal to 90 degrees, then just by subtraction, we know that this has to be a 60-degree angle, which makes this a 30, 60, 90 right triangle. All right, so this triangle here is 30, 60, 90. And we just learned some facts about the 30, 60, 90 right triangle, specifically a way in which we could determine the lengths of the sides. All right. Now you look at that and you say, well, why would it be important to learn the lengths of the sides here? Well, the coordinate value is a horizontal distance followed by a vertical distance. If I can figure out this side followed by this side, then I'd have my coordinates. All right. So that's what I need to do. Now my 30, 60, 90 right triangle rule tells me that I'm going to have one unknown leg, and that's going to determine everything else, right? So we kind of go back to this information here and we say, all right, I have my 3 pieces of information. I got an x, a radical 3x, and a 2x. All right. Those are the 3 pieces of information that I'm working with, one of which is the hypotenuse. That would be the 2x. The other 2 would be, under normal circumstances, interchangeable. However, that vertex angle up here was the 30-degree angle. That's opposite the x. All right. We have that corresponding relationship. So this side has to be x, and this side has to be x radical 3 or radical 3x, however you want to write it. I'll write it as radical 3x. All right. Now, the whole point of what we did over here is to not have to use the Pythagorean theorem again. All right. So if I know that the hypotenuse has to be equal to 1, and we know that because this is a unit circle with a radius of 1, which means that the distance from the center, so here's the center, and here's a point on the circumference, that distance is always going to be equal to 1. I now have a way of relating the 2x and the 1, which now tells me that x, if I solve that, x has to be equal to 1/2. All right, which fills in everything else, because if I know that x is equal to 1/2, I now know the height. And I now know, radical 3 times 1/2 is going to be radical 3 over 2. So I now know the horizontal distance, right? So you go from the origin to a point in space, it's always x comma y. Distance from the y-axis followed by distance from the x-axis, right? So this value here is the distance from the y-axis. That's the x. And this value here is the distance from the x-axis, which would be the y value. Right. So I'll use this little bar as a fraction here. So radical 3 over 2 and 1/2. Right. So that's a lot of work to come up with just one coordinate. It's like, all right, so we'll be here until midnight figuring out this, like we just got to do a couple more computations, and then we rely on symmetry, which we talked about a lot in the first unit, to help us go the rest of the way, right? But in order to do that, I need to figure out the second important angle, which is 45 degrees. All right. Now, none of these angles here involve a 45-degree measure. So we're back to scratch here. Right. So I'm going to draw another triangle. All right. I'm going to draw another triangle here. And I'm going to make it look a little different. Well, equally crappy, but a little different. Not ideal. This one's going to be an isosceles right triangle. This is supposed to be a right angle. This will give us a 45, 45, 90 right triangle. I use dashes. I was just checking. Sometimes I use colons. So, all right. In a 45, 45, 90 right triangle, or in an isosceles right triangle, the two legs are congruent, but that's it. All right. So these two sides I know are going to be equal in length to one another. So I'll call one of them x. If I call one of them x, I got to call the other one x. That's fine. That's easy enough. Now I need to figure out the length of this side here, which, for lack of anything better to call it, I'll just call it c. A squared plus b squared equals c squared. It's the hypotenuse. Why not, right? So that would be x squared plus x squared is equal to c squared. All right. X squared plus x squared is equal to c squared. Now, I have like terms here. X squared plus x squared is 2x squared. Take the square root of both sides. I hate that. I'm just going to rough it. Take the square root of both sides. The square root of 2 can't do anything about that, so I just call it radical 2. But the square root of x squared, I can do something about that. That's just an x. And the right side is just a c. We're ignoring any negatives here because we're talking about a geometric figure. Because when you take the square root, it's normally plus or minus. But since we're talking about a geometric figure, we don't expect it to be negative in length. Right? So we just kind of leave that off. Right? So the c value, the hypotenuse of a 45, 45, 90 right triangle would be radical 2 times x. Right? So I'm going to move this triangle out of the way here for a second, the one I drew earlier, because this diagram is going to get out of hand pretty quick with everything overlapping. I'll bring it back, but for now, I'm just going to move it out of the way. I guess I never really needed this or this. Kind of need this. All right. So using this information, I'm going to draw another triangle at the 45-degree location. Again, we're sweeping through a 45-degree angle. So this started off at the origin, or not at the origin, but it started off at the x-axis, and then it rotated up to 45 degrees. And that's where we landed. All right, so it swept through a 45-degree angle. Then what we do is we drop an altitude. And we create a triangle out of it. All right. Color do I use here? Okay, so I'll go green. So this triangle, again, was swept through or sweeping through a 45-degree angle. So each one of the non-right angles is going to be valued at 45 degrees. This one definitely 45 degrees. The other one, because all three angles have to add up to 180. All right, so I got 90, I got 45, that gives me 135. Subtract from 180, the missing angle has to be 45 degrees. All right, so I have that taken care of. And I also know that the two legs of this triangle have to be valued at x, with the hypotenuse being radical 2 times x. All right, now again, it's a unit circle. It's a circle with a unit radius of 1. So that means that this hypotenuse value has to be equal to 1. Therefore, x has to be equal to 1 over radical 2. As in, divide both sides by radical 2. So I actually know the length of the two sides now. All right. However, most people, for whatever reason, don't write it that way because somebody along the way decided that having a radical in the bottom of a fraction was a bad thing. That person, I never met them, but I can't imagine that they're very well liked. Either way, they're not right. You can absolutely have a radical in the bottom of a fraction, right? However, anytime you look up a unit circle online in a textbook, whatever, it's going to be in a different form. So we're going to rationalize this by multiplying the top and bottom by radical 2. All right, to clean out that radical on the bottom because some schmo along the way said that was bad. All right. So 1 times radical 2 is radical 2. Radical 2 times radical 2 is just a 2 because radical 2 times radical 2 is radical 4, which is 2. All right. If you're ever in doubt, Desmos is a good resource. As I typically say, 1 divided by radical 2 gives you this disgusting decimal. But the more you do a trig, the more you start recognizing some of the disgusting decimals. All right. So you see that one come up pretty frequently and you start to recognize it for what it is. But also, radical 2 over 2 gives the same disgusting decimal. So they're equivalent. Right. Since I know x is equal to radical 2 over 2, I know each of these two legs of the triangle are equal to radical 2 over 2. All right. And since I'm looking for a horizontal distance followed by a vertical distance to give me a coordinate value, I now have enough to determine that the coordinates here would have to be radical 2 over 2, comma, radical 2 over 2. All right. So it's horizontal distance followed by vertical distance. That's how it all works out. All right. So there's a lot of extra funk going on in here, but it's pretty manageable. It just takes a little getting used to. And this prior knowledge is so incredibly important. So the thing is, I say that this is manageable, but it also kind of operates under the assumption that there's a level of proficiency with some of this material. Right. Now, you may not know the unit circle, but I can't imagine you got to this class without knowing the Pythagorean Theorem, right? So that's at least a bare minimum. Rationalizing denominator, stuff like that. Those are all, things that hopefully aren't thrown in for too much of a loop, right? But now that we have this information, we can start filling out the rest of the unit circle, and it's not going to take us 40 minutes to do that. Right? It's going to take us like 5. Well, I'm a little long-winded, so maybe 7 minutes. All right. So I could bring this diagram back into the picture, literally and figuratively. Like I said, look at that, it's a mess. All right, all those numbers just kind of jumbled around everywhere. All right, so that's one of the reasons why I didn't want to have it all in there in one shot to begin with. All right, but in fact, I didn't even line it up the right way. So that's where I want it. All right. So the next angle is going to be a 60-degree angle. This is where it all starts taking off in a good way. All right. Because a 60-degree angle, and if you just kind of play this out, I would draw a triangle, and that triangle would have a reference angle down here of 60 degrees in this neighborhood. which would force a 30-degree angle up here. I'm going to erase all that in a second. Same parameters as the first triangle we drew, the blue one, which means it's going to have the same ingredients, but everything's in the reverse order. So it logically follows that the coordinates would be in the reverse order. So instead of radical 3 over 2 comma 1/2, it would be 1/2 comma radical 3 over 2, because the roll of 30 and the roll of 60 degrees got reversed. So everything corresponding with those values would also get reversed. So you're already able to draw a nice conclusion without having to really do any kind of work, right? Just reasoning it out, which is kind of nice. The rest of the unit circle is going to be along those lines too. In fact, I'm going to get rid of this line because that's a little messy. All right. So at 90 degrees, that's a straight upward movement. Coordinate 0, 1. Just by looking at the picture or looking at the graph, you can get that one. All right. So we're not worried about that one. But then when we go into the second quadrant, things start taking off in a nice way, because everything in the second quadrant is a reflection of everything in the first quadrant. All right. So in case you've forgotten, this is the first quadrant. All right. We usually just call it Roman numeral 1, but I'll put a Q in there in front of it. Quadrant 1, quadrant 2, quadrant 3, and quadrant 4. In the past, the quadrants didn't really matter too much, but with the unit circle and anything trig, they will absolutely matter, right? Incredibly so. So every coordinate in the second quadrant is going to be a reflection over the y-axis of every coordinate in the first quadrant. All right. So notation wise, it's a little weird to write, but it's basically saying, and I'll just jot it down here. The Q2 values are equal to a reflection over the y-axis of the Q1 values. All right, coordinates. You know, values could mean so many things, right? A reflection over the y-axis. So if you think about a reflection over the y-axis, if you don't know the rule, that's fine. You can still kind of figure it out, especially with a graph. You take a coordinate that's in the first quadrant. I'll just turn this one off real quick and show you. Let's say you have a coordinate at, I'll keep it simple, 1, 1. And I want it to go across the y-axis, right? I just want to flip it right over the y-axis. I would take that one step to the y-axis and then take the one step again beyond the y-axis. Same distance away from the y-axis, but on the other side, right? So that would put me at -1, 2, -1, 1. Right? So these 2 points are reflections over the y-axis. Now, if I thought it was something else, I'd put it into Desmos and I'd see very quickly that it's not. Maybe I thought I negated the y value, you know, reflection over the y-axis, negate y. But then I see very quickly that that's not what I wanted to do. That's a negation over a negation of the y, giving a reflection over the x-axis. All right. So it's the case where we take the 1 and negate it. And that gives us a coordinate in the second quadrant, or a reflection over the the y-axis. Now you can do this in general terms. Show you really quickly. Oops. Well, I guess I didn't really need that stuff. You take a coordinate a comma b. Create some sliders. Always comes down to sliders. So take that coordinate. If I want to reflect it over the y-axis, I negate the a, whatever the a value is. All right, this would be a reflection over the y-axis. All right, so reflection over the y-axis. So if I take my A value and just kind of move it away, you're like, oh, where'd everything go? Zoom out. I got my reflection over the y-axis. Zoom out even more. All right, it's still a reflection over the y-axis. I can move it up, I can move it down. It's still a reflection over the y-axis. All right, so all of that is my way of saying, take every coordinate that we just wrote in that first quadrant, duplicate it, or copy it. Get out of here. But make the x value negative. And now I have all those coordinates. I do have to be thinking about, well, okay, that's cool. I got all the coordinates, but what angles do they correspond to? Well, it's the same angular movement. You know, like I regret erasing my line here. I'll bring it back in. If I take this line and rotate it around, I get here 30 degrees. Here 45 degrees, here 60 degrees, and here 90 degrees. All right. But if I start over on the left-hand side, all right, I'm still moving 30 degrees, 45, and 60 degrees, and then 90 degrees. All right. I'm just moving backwards. All right. So 30, 45, and 60 backward from 180. All right. So with that in mind, I could then say, all right, well, this one would have to be a 30-degree angle, 30-degree reference angle, but in this direction, which would make it 150 degrees. The second one would be a 45-degree angle, but in that clockwise, in a reverse direction, making it 135. And this one, 60-degree angle in the reverse direction from 180, dialing it back 60 degrees would be 120. So we have those angles. We got those little dashes there. We'll have to get into that in a little bit. But for now, we have angles and we have coordinates, and we did it much quicker, much quicker than we did it previously. All right. So now we have all these coordinates in the northern hemisphere, if you will. I need some in the southern hemisphere. It's still the same 30, 45, and 60 degree reference angles, though. So I can build off of that. So 180 plus 30 is 210. 180 plus 45 is 225. 180 plus 60 is 240. Same idea in the fourth quadrant, going backwards though, 30, 45, and 60, but dialing it back from 360. So 330, 315, and 300. And so all those angles, they just happen really quickly. When I go to fill out a unit circle, when I need to scratch one out by hand, it's not very often, you know, as a teacher, I don't really need to write it out by hand except in situations like this. I just remember that it's always a plus 30, 15, 15, 30 progression. As I work my way around the circle, starting with 0, add 30, 15, 15, 30, then do it again. It's periodic, so the pattern should continue. Add 30 again, 90 plus 30 is 120, plus 15 is 135, plus another 15 is 150, plus another 30 is 180. Add 30, 15, 15, 30. I mean, one way or another, you got to memorize something. It's just a question of what you choose to memorize. All right. So then we need to reflect all the coordinates in the northern hemisphere over the x-axis, right? So to reflect over the x-axis, we take our original coordinate, a comma b, but we negate the y value. So that's a reflection over the x-axis. All right, so you can see, I mean, it's a little on the funky side, but as I move, a little double tap there, as I move my a value, the reflection over the x-axis follows along with it. Same thing with the b value. Wherever I put my coordinate in the first quadrant, so this is the original. Wherever I put my original point, the reflection mirrors that movement, right? So it's telling me to negate all the y values, long story short. So, oh, that's not my lasso. Lasso. We take all these values here. I'm going to place them appropriately according to their appropriate reference angles. So this one goes here. This one goes here. And this one goes here, but I'm going to negate the y values now. I'm going to tuck in a little minus sign. And then I'm going to do the same thing for the values in the first quadrant. I'm going to flip those over the x-axis by negating those y values. Oh, got a bit of the triangle there. I don't want that. All right, so here. Oops, hello. I don't need all that. Here for a sec. So again, I'm going to negate all the y values. So they were positive, they're all going to become negative now. And so now I have a complete set of coordinates around the unit circle. Oh, I missed a couple. So the one on the x-axis, go back to the original diagram here. On the x-axis, we have a -1, 0, and we have a 0, -1. All right, so -1, 0, which makes sense because we're 1 unit away from the origin to the left. That should be on the x-axis. Y value is equal to 0. We're 1 unit away from the origin down. That should be on the y-axis. Right? And so that would be 0, -1. All right, so we have a complete list of coordinates. And, you know, if you don't have any experience with the unit circle, it's like, okay, cool, we have coordinates. It's great. Why? All right. Oh, by the way, we can get rid of this. This is a typo that's been living on in infamy for so long. These where it says positive, negative, you can just ignore that. I've been erasing these for years now, but not in the master document. And so here we are. And it says typo for somebody. Let's go back to blue. All right, so every coordinate on a unit circle is the result of cosine comma sine. So we have x comma y is any point in space could be represented by a coordinate x comma y. But if I tell you that on the unit circle, that corresponds to cosine of theta comma sine theta, where theta is an angle between 0 and 2 pi, or 0 and 360 degrees. That starts to shed a little light on the value of something like this, because what it tells us is what the cosine and sine values are at, oh, I lost my, let me undo that. Cosine and sine values are at a variety of locations around a circle, right? But more importantly, it tells me what the cosine of a particular angle is in a simple form. And there are ways to build off of that to come up with clean representations of something that might not otherwise seem clean. Like, for example, I'm spinning around this unit circle here, and I'm seeing all of these disgusting decimals. You know, I get to this location here, which might be around a 45-degree angle, right? Looks roughly like it could be 45 degrees, just kind of ballparking it. But if I tell you that I want the actual coordinates at 45 degrees, we already have that. That's radical 2 over 2 comma radical 2 over 2. All right, so coordinate wise, radical 2 over 2 comma radical 2 over 2 is a nice clean representation of that point, which Desmos is rounding to a disgusting 0.707 blah blah blah. So we can get clean answers out of this, right? So that's one thing, right? So there's that. Now, if I tell you that there are relationships between sine, cosine, and the other types of trig functions like tangent, cosecant, secant, and cotangent, then from this one unit circle, for all of these angles, we can now determine all 6 trig ratios based off of this information, right? So that's the power of this. Just by identifying the x value of a coordinate, I now know what the cosine is at a particular angle. So for example, at this location here, right, I'll highlight it in the light blue. I have an x value of radical 2 over 2. What that means is that the cosine of the angle 45 degrees is equal to radical 2 over 2. All right, radical 2 over 2 we know is a disgusting decimal of about 0.7071, but I'll put it in anyway. All right, cosine of 45 degrees, let me just put my calculator in degree mode. So I hit that little wrench there at the bottom. You have a choice between radians and degrees. I'm going to put it in degrees. Go to trig, cosine, 45, same disgusting decimal. All right, but one of them is a nice clean radical 2 over 2, and the other is just a disgusting decimal. All right, so that shows you a little bit of the benefits of it. But what happens is in the classes that follow, like all the calculus classes, you know, we take analytic approaches to a lot of this, a lot of the calculus content, and that involves you being able to manipulate trigonometric expressions and use the results in a clean way. Otherwise, you get bogged down with decimal values, and the rounding that you would have to do introduces an unacceptable amount of error, and you're not able to draw any meaningful conclusions. All right, so so that's that. But what we need to do is get the radian measures now. All right, so the radians. So you're getting like a month's worth of content all in like one lesson here from last semester. So this is all the stuff that I need, that I really needed you to know coming into the class. But like I said, your future would be, mathematically anyway, would be in doubt like serious jeopardy if you don't know this stuff. So that's why we got to take the time and do it. And so it wasn't originally my plan to spend an entire class session on the unit circle, but you know, you got to do what you got to do. Can't take the chance. Can't have you sitting in
what class would have this? Because I've taken everything up to the point where I can have your class, so I don't understand.
college algebra with trig.
That's 135, right?
That's the class that comes before this one. I honestly, I can't remember. I think it might be.
Yeah, but they didn't teach this at all. Like,
I can second that. We didn't go over this at all. I remember senior year of high school, however long ago that was, we were doing like, you know, SOHCAHTOA and all that for trig. And I learned a little bit of this, but I have not seen it since then. I mean, maybe that's a failure on that professor's part.
Or, you know what? I think one of my professors said that they canceled 135 and changed it to something else. I was actually going to ask you at the end of class about that because I looked it up last semester and this semester. They don't offer 135 with trig anymore. And it says from my particular major that I need to take that.
Yeah, so what they did was they just dropped the with trig from the title. So college algebra is college algebra with trig.
So I'm so sorry to take up any time in the class, guys, but this was going to bother me anyway. I'm required for certain civil engineering courses to have 135. Does that mean that 130 or 131, whatever was prior to this, that they dropped the trig on, is that going to cover the requirement?
That was the prerequisite. Oh, sorry. I think if that was the prerequisite to this, then as long as you have this, you should be fine moving forward.
Interesting. Thanks, guys. I'm sorry. Like that's been really bothering me because I don't know how much more math I have. And this is
a lot of that's one of those where you might want to reach out to the curriculum chair, or I mean, you could reach out to Dean Houston, but really just, I mean, you're going to want to get the answer to that one because like the counselors, they don't really know at this point because there's a lot of changes happening with curriculum in the department. So I would reach out directly to the curriculum chair or Dean Houston, either way.
Thank you. I'll do that at the end of the semester because if I have to take more math, I might blow my brains in. This is really, and if you're not teaching it, then I'm really going to be upset.
Fair enough. All right. So the last little bit would be the radian measure, right? So a radian right? So I'll just tell you, because you don't really need to write the definition, but I'll just tell you that it is a distance around the circumference of a circle equivalent in length to the radius of that circle. All right, so it's kind of a weird concept, but what that boils down to, I mean, I just, in an in-person class, it's easy to demonstrate because I have one of those bendy rulers, and I have a ton of them, but you know, even ones that aren't bendy, I just bend it and hope it doesn't break, right? But what I would do is I would measure the length of the radius and then just wrap that length around the circumference of the circle. It's not going to cover the whole thing. It'll only cover part of it, right? So you only get like a little segment of the circle that's covered by the length of the radius. And then we would see how many of those little segments would it take to make up an entire trip around any circle. It doesn't matter, right? It turns out that there are 2 pi radians at about 6.28 radians or radius lengths necessary to wrap around a circle. All right. So there are 2 pi radians in a circle. There are 360 degrees in a circle. Therefore, the conversion factor would be 2 pi radians is equal to 360 degrees. And from there, we can make a conversion because if I divide both sides, and really there's multiple conversions that we can make, But if I divide both sides of this equation by 360, I get pi over 180 radians is equal to 1 degree. All right, because we're thinking of the degrees as kind of like units. In fact, let me rewrite the degree. Actually, I'll write it out. Degree. So it's really the 360s, the number values that divide out, but you're left with a result, 360 divided by 360 is equal to 1. Right? And so that gives us a conversion factor, and it allows us to determine the radian measures equivalent to every one of these degree values. Right? But we use our knowledge of ratios to help us kind of go the rest of the way. Because what we could do, for example, I got this number right here. I'll just start with this one. If I need 240 degrees, what I would do is I'd multiply by 240, multiply by 240. And it would be terrible. Because then I'd get 240 over 180, which I then have to simplify. And eventually you'd get 4 over 3 with a pi. So that would tell us that 240 degrees is equal to 4 over 3 pi radians, for example. All right, so you could do it that way. It would just take forever. We tend to write that as 4 with the pi on top over 3, just to make it a singular fraction. But, that's really up to you. You could write 4/3 pi or 4 pi over 3. All right. We definitely don't want to do it that way, because if you have to crunch out those numbers for every single value on the unit circle, it kind of defeats the purpose of creating the unit circle as a tool or a reference tool for you to simplify your understanding of trigonometry. Right? Because just look at this. You just take a look at this page, and the first thing that you're probably asking yourself, or I would be asking myself, is how the hell is this making anything simpler? Looks like it's making it more complicated. The idea is that we can swiftly create the unit circle if we know what the relationships are. All right. And so next class, I'll show you how quickly you can create the unit circle, and then and you'll start to see some of the benefits of this. Right. But let me just kind of take it back a second here to this idea that 2 pi radians and 360 degrees are equivalent to one another. Right? That's the key fact. If you know that, then you know what you need to know in order to figure out everything else. All right, so I'll use this one. This is the key fact. All right. So I know that this one has to be 2 pi. Right, those little dash marks, those represent the radian measure. So this one here, 2 pi, easy enough. All right. If 2 pi and 360 are equivalent, well, 180 is half of 360. So its radian measure should be half of 2 pi. Half of 2 pi is pi. All right. 90 is half of 180. So the radian measure for 90 should be half of that of 180. So half of pi, or pi over 2. So I'm just going by halves now. Because 45, for example, is half of 90. Half of pi over 2. Well, half of a half is a quarter, so pi over 4. All right. So if I want to work my way around the unit circle here, filling in all the other pieces of information, I want to use some idea similar to that. Like, for example, I'll even use 30. Forget 60 for a second. The 30-degree angle. Well, 30 is 1/6 of 180. Right? If I want to get from 180 to a 30, I would divide by 6, right? So pi divided by 6 should be this angle. Knowing this information allows me to kind of build out the rest of the way, because 60 is double 30. So double the pi over 6. 2 pi over 6 simplifies down to pi over 3. So looking at the relationships between the first quadrant angles would actually help us figure out everything else, because, for example, 120 is double 60. So double my pi over 3. So 2 pi over 3. 135, that's a weird one. If you don't know off the top of your head that 135 is 3 times 45, then you wouldn't necessarily realize that all you have to do is take pi over 4 and multiply it by 3, and you get this value. However, now that you see it, hopefully it's something that would resonate and you'll think about it from here on out. 150, well, 30 times 5 is 150. So take the radian measure associated with 30, which is pi over 6, and multiply that by 5. So pi over 6 times 5 would be 5 pi over 6. All right. Noticing trends is a really important aspect when it comes to trigonometry, because it's a periodic relationship. You notice the trend repeats itself over and over again. Like, for example, I notice that all of my denominators are 6, 4, and 3 as I move away from the x-axis for the radian measures. That's great. 6, 4, I already have the 3 there. 6, 4, 3. All right. On the y-axis, denominator is equal to 2. 6, 4, 3, 2. Then 2, 4, 3, 2, 3, 4, 6, depending on where you're starting from. So this denominator would be equal to 2. All right, so following that same pattern. All right, 0 gives you 0, so I have that one. 0 is 0, no matter what the units of measure in terms of angles. But the top numbers are what matter now. So looking at 210 degrees, 210 is, well, if I start off with a 30, 30 times 7 is 210. So 7 pi over 6. All right. Now, you look at the relationship between the numbers that make up the fractions. In the second quadrant, you see in each case, the numerator is exactly 1 less, in terms of the coefficient, is exactly 1 less than the value in the denominator, right? So the coefficient in the numerator is 1 less than the denominator. All right, for the radians. So if I know it's a 6, 4, 3, and I know that the numerator is going to be 1 less than the value in the denominator, the coefficient, then I know it's got to be 5, 3, and 2. All right. That doesn't seem to be playing out the same way in the third quadrant, but there is a relationship, because after I figure out the first one, it's like, okay, well, the coefficient is not 1 less than the denominator. In fact, it looks like it's 1 more than the denominator. So this one would have to be 5 pi over 4, right? Because I had a 6 becoming a 7. I had a 3 becoming a 4. So it would make sense that the 4 would become a 5. All right. The last one we could try to investigate and figure out, but I can tell you that that's the weird one. So you're either going to figure that one out by formula or by multiplying. But I can tell you that the rule is, it's not quite as pretty. All right. The coefficient is double the denominator minus 1. So 2 times the denominator minus 1. That's easily the strangest one out of all of them. All right, so if I take the 3, double it, I get 6 minus 1 is 5. So 5 pi. 8, double it. I'm sorry, 8 double it. 4 double it, you get 8 minus 1 is 7. 6, double it, you get 12 minus 1 is 11. And you could do a quick double check on that. Like, for example, 5 pi over 3, that's 300. 300 is 10 times 30. So 10 times pi over 6. 10 6 reduces down to 5/3. All right. So that's the whole unit circle. Okay, it crashed. I'm going to open it up again in a second. Just bear with me here. Let's make the word of the day unexpected. Unexpected is the word of the day. I don't always have a reason for selecting any word of the day. It's just in this particular instance, it feels like there's a lot of unexpected things happen, you know, like the app crashing, spending an hour and a half on a 5-minute lesson, you know, things like that. All right. So
Professor, I have a quick question.
sure.
Will we be seeing some of this on the upcoming test, or is it just on the practice test that we took?
It's just a practice test, but this is going to feed into being able to handle the trig parts of it.
Okay, thank you.
No problem. So that's the unit circle. The bottom, it says state the six trig ratios. It said sig, like 6 trig. I put it all together. Sine is opposite over hypotenuse. You know, it's SOHCAHTOA. So opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. All right, that's all stuff you're familiar with. A consequence of tangent being opposite over adjacent, it's always, well, that's true, but it's also, is the word I was looking for, the result of taking the sine function, sine of theta, and dividing it by cosine. All right, so that's equivalent. If I take tangent, the tangent ratio opposite over adjacent, or if I take the 2 separate ratios, opposite over hypotenuse and adjacent hypotenuse, and divide them, I will get the same thing. All right. Cosecant is hypotenuse over opposite. But a consequence of that is that it's a reciprocal of the sine function. Secant is hypotenuse over adjacent, which gives a consequence of 1 over cosine. And cotangent is the reciprocal of tangent, adjacent over opposite. All right, so, oh, dang it, that crashed on me. I made that up. It didn't crash. I accidentally hit the wrong thing. I don't know why my instinct there was to like cover up a mistake. That's so weird. Actually, the most honest person I know. Anyway, I'm actually honest to the point where when I lie, I immediately fess up to the lie. So anyway, I didn't want to stop the share. I wanted to stop the recording